Soil health and organic matter are critically linked, and in many ways, we can think about soil health. I don't really think this is a fair statement to say that soil health is just a repackaging of fostering organic matter, but I think there's a lot that happens or has to do with soil health and organic matter. Organic matter is critically important for the health and functioning of a soil. Okay, so most of you have had a soils course at some point, but we all understand and farmers inherently know the value of organic matter. It really is the foundation for a productive soil. Organic matter and soil carbon can, we use those terms, although they mean different things, we use them kind of conceptually the same. Roughly, organic matter is 50, 55, some odd percent, depending on the soil and the type of organic matter, but 50% carbon, organic matter is about 50% carbon. It's made up primarily from plant residues, but also from microbial and animal products and byproducts, okay? The thing about organic matter is on a weight basis, it typically only makes up a few percentage, almost, for most soils in Ohio, mineral soils that is, organic matter is usually just, say, 2, 3, 4%, maybe 5 or 6, 7% of the weight of that soil. So it's a small percentage, but it plays a very large disproportionate role, okay? And you likely know all of these things, but I'll just provide them here for you. But what does organic matter do? Well, it has physical benefits, chemical benefits, biological benefits, right? So it enhances aggregate stability, water infiltration, soil aeration, and air and gas exchange, water exchange, reduces runoff, improves water holding capacity, all these things from the physical perspective. Chemical benefits, part and parcel to this course is the buffering capacity of the soil and the ability of that soil to supply essential nutrients to crops, right? Biological benefits, providing the feedstock or the base or the foundation for living organisms in the soil. It enhances soil food webs, which can help suppress disease. There's a lot more that could be written about biological benefits here, as well as others, but it transects across the physical, the chemical, and the biological properties of soil. It has very vast and far-reaching effects in terms of how that soil functions and the overall health of that soil, okay? So the importance of soil organic matter and soil quality, soil health cannot be overstated, okay? Here's a bit of a redundant slide, but it's kind of saying the same things. A table from our Haviland textbook showing, the property, what does it do, what is the effect on soil, the effect on plant, et cetera, et cetera. So these, again, should be a bit of a review for most of you, all right? Total organic matter is commonly measured. We've talked about this in terms of what makes up a soil test. So the way this is done commercially, there's different methods to measure organic matter, but the way that this is most commonly done commercially is a method called loss on ignition, okay? And so what that really entails is weighing a oven-dried soil into a crucible, calculating the mass of that soil, and then putting that crucible, these heat-resistant little porcelain cups, into a muffle furnace. And typically, they're gonna heat that at around 375 degrees for 2 hours. That temperature does matter and does have an effect on that, on your total answer. But 375 for 2 hours is what is typical in Ohio and the north central region. They take those crucibles out of the oven, they let them cool, reweigh them, and then this loss on ignition, or LOI, is really an original weight minus the final weight. So weight before it was heated weight after it's heated, and then you divide that by the original weight. So it's essentially just a percentage of mass lost. Now at 375 Celsius, that's very hot, right? And a lot of that organic matter is essentially burned off. That's the whole idea, is that you're combusting that organic matter, and then as a measurement, it's going to tell you how much total organic matter was there. So this measurement is cheap and simple and rapid. Commercial labs do it all the time. It's inexpensive, but it's not as sensitive as a total organic carbon or a total carbon from a combustion analyzer. And I'll leave it at that. We can get into some more methodology, but the total organic matter is often considered a different measurement than total carbon. Okay, so even though we use organic matter and carbon the same, they might be measured a little bit different, or there's a few different methods out there, and this LOI is the one that when you encounter soil tests, unless it's from a research lab, this more times than not is going to be the measurement that they use. Okay. So total organic matter is really important. We all understand that. But, we think about why that is, right? Like, why do we care so much about organic matter? And I just like showing this slide because it shows you how a very, very long time ago people really understood or had at least some rudimentary understanding of the nature and property of organic matter. So I'll read them to you. It is the decay of organic matter, not its mere presence, that gives life to the soil. Okay, so this is 1910. And then William Albrecht said in the late 30s, attempting to hoard as much organic matter as possible in the soil, like a miser hoarding gold, is not the correct answer. Organic matter functions mainly as it's decayed and destroyed. Its value lies in its dynamic nature. Okay, so it's the idea that we can't just compile organic matter and hold it into a bank account, right? Like in the soil. We need that organic matter to be cycling and turning over, destroying, decaying, and getting replaced for that soil to function at its best. All right. So let's explore this a little bit more. Okay. Ecologists or soil scientists can go out and measure. Take carbon budgets, and they can measure things like an annual soil carbon flux. Okay, so we can think about carbon inputs coming into the soil, such as shoots, roots, or exudates. And then we can think about the existing pool of organic matter in the soil, and a small amount of that might be from new inputs. And then our carbon outputs come as CO2 from respiration. So the actual degradation of reduced carbon, it's oxidizing carbon, chemically, in microbes and plants, etc. It's an aerobic respiration process, and that CO2 goes back into the atmosphere, right? So CO2, this is the circle of life, right, guys? It's like CO2 gets fixed into plants, it gets translocated into the roots and into the soil, and then via crop residue, etc., that gets oxidized, burnt up for the chemical energy in those cells through respiration that you and I participate in daily, and that CO2 goes back in the atmosphere. So, we can think of this as synonymous with inputs as stabilization, which is, we can think of building a wood pile, for example, reduced carbon in wood, and then mineralization or respiration when we burn that wood pile. Okay, so we do this chemically for the energy in that reduced carbon. That's why that's the foundation of cellular respiration, right? And so a big part of this is like this happens regardless if we wanted to or not, but carbon goes into the system and carbon leaves the system. The challenge is, or like the rub here, is how much goes in versus how much leaves, and the rate of it going in versus the rate of it leaving. Okay, so and then if we have a little bit of new carbon every year getting added to that system, we are in a period where organic matter is being built, right? And if there's a little bit more carbon that leaves and gets put in every year, then of course we're in the opposite category of we're losing a little bit of organic matter every year. And these are processes that happen over decades. It's one of the challenges of organic matter. So when we measure total organic matter, we're measuring this whole pool, right? This loss on ignition, it's this whole pool that we're measuring. And it takes time to detect that. There's a lot of carbon in the soil, there's a lot of organic matter on a poundage basis, or a ton basis, or a hectare or kilogram basis. And so it takes time to actually measure those differences. And so what we do is, well, we've already discussed this, but just to be clear, stabilization, it's nutrients and carbon from an inorganic form to an organic form. So we talked about this in nitrogen cycle. We can think about this as immobilization. So we're locking up organic matter and we're building organic matter. And then this idea of mineralization is converting organic matter from an organic form to an inorganic form. So we're respiration, when we respire and destroy organic matter, decompose organic matter, we get nutrients that are released. Okay, because there's nutrients locked in that plant biomass, in that organic matter. Okay, so these are important processes. And thinking about this, in the nitrogen cycle, we talk about immobilization versus mineralization. Here, we're calling it stabilization, carbon stabilization versus mineralization. So, it's very similar concepts here, but maybe thinking about carbon versus nitrogen in this context. So, total organic matter changes very slowly, right? So, as soil scientists, we think of different ways that we can study organic matter. And one of the ways that we do is we conceptually break total organic matter down into two and often three different pools, okay? And so these are, represented here by these three slices of the pie: passive, slow, and active. The passive represents the largest fraction of organic matter. It's typically not plant available and it cycles slowly, okay? It can be organic matter here, the carbon can be decades to centuries old. We have a slow pool, which is intermediate in terms of cycling and in terms of age, typically representing anywhere between 10 to 30% of the total organic matter. And then we have an active fraction. And this is often recently deposited organic material, so like root residue, root hairs, root exudates, things like that, microbial cells. It's characterized by rapid decomposition and cycling. And in terms of its turnover, it's usually not very old of material. In other words, it's turned into organic matter and it cycles out relatively quickly. Okay, so reality is this active pool, 5 to maybe 15% of the total organic matter. So it's the smallest slice of the pie, but it's very, very important. Okay, and so we'll get into that right now. So, and this is, very, the reality is that all this is conceptual. Okay, so what I'm telling about these three pools, it's more about how we can study and think about organic matter. The reality is there's not three unique separate pools, but it's the way we measure those pools, and they're operational. Again, this idea of operationally defined pools. But we can think of these different pools as having different functions. Okay, so the passive pool might be more important for CEC and water holding capacity. The active fraction important for available and rapidly cycled nutrients, microbial biomass, biological activity, etc. So this active pool, especially for the purposes of this class and soil fertility, is critically important from a plant nutrition perspective. and that's why we're talking about it here and spending some time on it. Now, there's lots of different ways that we can measure this active pool, and you'll see this word labile, and that just means it's chemically available. So it's not in some form that's really hard to degrade. It's going to be relatively available, biologically available. Now, again, we measure this total pool commonly in a grower test by loss on ignition. But when we're thinking about quantifying the active pool, there's various ways that we can do that, okay? And so some of them are listed here. Some of them are expensive, and some of them are relatively inexpensive. So we're not going to get into all those details, but we certainly could talk more about that if folks were interested, okay? So the active fraction is a small fraction, typically 5 to 10%, up to 15. It's rapidly cycled. It can be difficult and expensive to measure, but when we're talking about a very productive soil, and again, the value of organic matter is not just in hoarding it like a miser, but really having it exist and break down and turn over rapidly. And when we're talking about that kind of dynamic, we want to increase the slice of this pie, the active fraction. We'd really like to, for a healthy functioning soil, we believe that it's very important for this active organic matter to, that pool size to increase, okay? Here's just a way to show you that active organic matter is a very, very small pool, okay? So we talked about organic matter being, say 2, 3, 4, 5% of a soil. Here is a couple measurements that active carbon respiration, microbial biomass carbon, percent of the total carbon, maybe 1, 2, 3, 4% of the total carbon in the soil. So we divide this by essentially 50%, or take 50% of that to get your organic matter. And then you take these numbers and you split them in half essentially. And then you figure that organic matter is just a few percentage of the total soil mass. So here, again, we're talking very, very small amounts of total mass that this active organic matter is representing. So just because it's small does not mean it's not important, right? So it's a small percentage, but plays a proportionally large role in nutrient energy supply. Okay. So it's important for me to kind of introduce that concept because it's this idea of active organic matter. It's really important for a lot of the things that we talk about and think about with soil health. Just want to we'll give you one slide about why active organic matter increases production potential. Okay. So here's a diagram where we have roots in the rhizosphere with associated microbes and associated active organic matter. Of course, these things are all very intimately and spatially integrated, not distinct little pools like we're showing in this picture, right? But when we increase our active organic matter, we essentially increase our ability of that soil to store nutrients and store them in a very available form, okay? So when we have a lot of active organic matter, we've got NPK, et cetera, et cetera, et cetera, all the essential elements that we talked about that are being held in that soil system like a sponge, okay? And so this idea that, there's been some nice elegant studies showing that when this pool is large, and say, for example, nitrogen demand increases, well, the plant is able to essentially access that pool. So it's like a bank account in some ways where you can make deposits and have that there, and then when times are lean, it can pull that out, make withdrawals from that active organic matter to get more nutrients out and continue to grow and thrive, right? So it's this idea of resilience, or however we want to frame this or think about this, but it's like there's a nutrient reservoir of available nutrients, and then as that active organic matter pool grows, that our nutrient reservoir grows too. So when times are plentiful, when nitrogen, say, when crop demand is low and we've just fertilized, if we have a very active organic matter pool, it's going to soak those nutrients up, less susceptible to leaching. And then again, when that crop demand really increases, then our active organic matter is going to be able to supply nutrients to that growing crop. Okay, so these concepts are all, maybe one and the same, but we can split them out. So tighter nutrient cycling. Okay, so more complex soil food webs are able to capture and cycle nutrients more efficiently. So, these things are highly related, but when we have trophic complexity and food web complexity, we typically have greater nutrient use efficiencies. And that means that as our active organic matter increases, our soil food web is going to increase and the complexity is going to increase. Maybe not always, but very commonly that occurs. And with that, we're going to have tighter nutrient cycling and greater nutrient use efficiencies. Okay. And then this idea of coupling nutrients to carbon. And this is a concept that's very important. We've talked already in this course about organic versus inorganic nutrients, organic nitrogen versus inorganic nitrogen. We add inorganic nitrogen in our nitrogen fertilizers, our conventional fertilizers, and it's like a very readily available source of N. If we add it in the form of manure, there's available N, ammonium and nitrate there, but it's got to get converted. Much of that organic nitrogen has to get converted to inorganic nitrogen to be crop available. Well, if that happens immediately, if that's available immediately, there's a lot of, as in the case of a non-coupled carbon to nitrogen fertilizer, if it's mostly ammonium nitrate, that's going to be subject to loss, right? But if it's coupled with carbon, say, as in the case of this active organic matter, it's going to be a slower release supply, okay? So it's going to rely on that soil biology to cycle and turn that over. Now that could, potentially be a problem if the crop demand is now. But for the most part, it depends on which side of the sword you're on there. But from a production perspective, it's going to provide nutrients not just in a big slug, but over the course. It's essentially a slow release nutrient. So it's naturally or biologically mimicking what, say, a nitrification inhibitor or some sort of urease inhibitor or some sort of nitrogen efficiency enhancing product. We know that when we put a big slug of N into the system, we're just using nitrogen as an example here. We can use a lot of other nutrients as well, but a big slug of it, it's susceptible to loss. This is a way that we can increase our efficiency by having it be more slow release as it's cycled through the soil food web and made available in that rhizosphere. Okay? So organic matter, very, very important for soil health. And thinking about not just total organic matter, but the active. Now, the passive and the slow pools are important in their own rights, but again, for the sake of this course, and this is a little bit of my bias coming in here, because I think about active organic matter a lot, and this is some of the measurements that we do, and I'll get into that in subsequent talks here.